general relativity, step by step. Now last time I was looking at what happens when r is less than 1, and the nature of the space-like and time-like coordinates, or the time-like and the space-like coordinates, swapped from being t and r to being r and t, which is a little bit odd. We're going to investigate what exactly that means in this and subsequent screencasts. I'm going to consider null geodesics, and I'm going to go very, very slowly because it's very easy to introduce. Mathematical infelicities into your thinking. So I'm going to consider null geodesics, radial ones. So that means that d omega squared equals 0. And of course, a null geodesic is ds squared equals 0. So I can just write out my Schwarzschild metric. So that's ds squared equals 0 equals minus dt squared 1 minus 1 over r plus dr squared over 1 minus 1 over r, provided that r is not equal to 0. If r not equal to 0, not equal to 1. If r equals 1, and I guess r is not equal to 0 as well, because if r is equal to 0, we've got these reciprocals to deal with. So that tells us that dt squared times, minus, no, I'm taking it over to the other side. So plus dt squared, 1 over 1 minus r. Of course, if you want to use geometrized units, you can say 2m if you really want to, equals, what have we got left? dr squared over 1 minus r. Oh no, it's not 1, it's 2m. It hurts to look at it. Look at that 2m, it's just sitting there. It's not doing anybody any good. Just choose units in which the Schwarzschild radius is equal to 1. Okay. That's okay, isn't it? R is not equal to 0, r is not equal to 1. But I'm not making any assumptions about r being greater than 1 here. So that tells me that dt squared equals dr squared over 1 minus 1 over r all squared. Are we in control here? Yeah, I can just take this bracket down there. So that tells me that dt equals, and now we've got to be a little tiny bit careful, plus or minus dr over 1 minus dr over 1 minus 1 over r. Alright, so we can integrate it. dt equals plus or minus. Now, of course, the plus and minus correspond to ingoing and outgoing light. When I was looking here, I just specified that ds squared equals 0. That's just a radial null geodesic, so I didn't care whether it was going in or out. But here we'll see that the ingoing and outgoing correspond to the two roots of this equation here when I remove the square. The integral dr over 1 minus 1 over r is not equal to 0 or 1. Equals plus or minus. So t plus a constant, just performing that integration there, is plus or minus the integral of dr times, multiply top and bottom by r over r minus 1, equals plus or minus the integral of dr over r minus 1 plus 1 over r minus 1, plus or minus the integral of dr over 1 plus 1 over r minus 1, equals plus or minus. See, I'm doing it step by step. I don't want to take too many steps off, because at some point I'm going to have to start considering what this integral of 1 over r minus 1 is, and I just wanted to be absolutely sure that I can trace my reasoning. That's r plus, now what's the integral of dx over x? Well, that's log of mod x, log the modulus of r minus 1. So you'll see that just by using this formula here, this nice formula here works for r is less than 1 or r is greater than 1 equally, because of this modulus sign here. Something quite astonishing, that. So t plus k equals that. So t plus k for the constant of integration is plus or minus r plus the log of the modulus of r minus 1, whether r is greater than 1 or less than 1. Now, and that specifies the path of null geodesics. Now, as it turns out, you can invert this formula quite easily. You can say that r equals 1, let me just write it out from my notes here, w of e to the, I'm using uppercase k, plus or minus t minus 1, where w equals the Lambert w function. If I say that y equals e to the x, that's the same thing as x equals log y. If I say y equals x e to the x, that's the same thing as saying x equals w of y, where w is this Lambert w function. I don't want to labour this point here. I just want to make the observation that we can take this nice geodesic equation and invert it so that r is on the left-hand side on its own. So we can feed it a value of t and read off the corresponding value of r. However, this system here works for r is, this system works for r, this gives answers for r is less than 1 or r is greater than 1. This system still works for r being outside the event horizon or inside the event horizon equally. It's a little bit hard to deal with. The Lambert W function is a bit of a peculiar beast. It's got branches and it doesn't quite behave itself in the nice, clean, clear way that the log function behaves itself, but still, it's a nice analytical solution. So we've got two sequences of answers here. We've got t plus k equals plus or minus r plus log of mod r minus 1. And again, that works for r is greater than 1 or r is less than 1. But what does it look like if you try to plot it? And I'll talk about that in the next screencast. Stop there. Stop.